Okay, English. Today we're going to count permutations, and on Friday we're going to count permutations. And this might be surprising to you because we already counted permutations. But we're going to do it anyway. And what's the idea? Let me start with a very simple analogy, which is that if you want to count subsets of n, we saw that there's 2 to the n of them, and so we could say that we already counted the subsets of the set n. Okay, but then we could introduce what's called a statistic, and a statistic is just like statistics for people, right? So maybe you want to know how many people there are in Colombia, so you count the number of people in Colombia. I don't know how many there are, maybe 40 million, something like this. How many? 45 already? I guess I've been out for a while. But then, once you count the number of people in Colombia, you want to know more. For example, you might want to know how many men, how many women, how many older than this age, how many younger than this age, and so we call these statistics. And with sets, it's the same thing. So what's a statistic for a set? For example, we could say the size is a statistic, and we want to know how many sets are there of size k. And so we saw that as n choose k. Okay? And so this is what we might call a statistic for sets. Okay? But of course there's many different statistics with people and with sets and with permutations. And so what I want to discuss in the next couple of classes is several different statistics that we can consider for permutations, and then we're going to do the corresponding enumeration. Okay? So maybe a good title for the next couple of classes is permutation statistics. Okay. Before we start counting, I'm going to go over here and talk a little bit about permutations and just kind of agree on some notation. So recall various notations for permutations. And the point is that there are several different ways of writing down a permutation, and they're all going to be interesting for us. So, and depending on who taught you these, maybe they have different names, but for example, what do we mean by two-line notation? This is kind of the easiest to read. So two-line notation looks like this. Okay. So what I mean here is that for my permutation pi, I have that pi of 1 is 3, pi of 2 is 2, pi of 3 is 6, and so on. So that's one notation. Now once you start doing this for more than 30 seconds, you get really bored of writing all of this because this is always the numbers in increasing order. So then one line notation, you just write the same thing but you omit the top row. So here we're considering the permutation as a word, and again it means that pi of 1 is 3, pi of 2 is 2, etc. Now the next notation that's very useful is cycle notation. So what do? What we do is that we start saying, okay, let's start with, for example, the number 1. And then we say, what is pi of 1? Well, pi of 1 is 3. So I write the 3 next to it. And then I say, okay, what's pi of 3? Pi of 3 is 6. So I write the 6 next to it. And then I say, okay, what's pi of 6? Pi of 6 is 4. So I write 4 next to it. And then I say, what's pi of 4? Pi of 4 is 1. And then instead of writing the 1 again, because I already have it, I close this cycle. And it's called cycle notation because pi of 1 is 3, pi of 3 is 6, pi of 6 is 4, pi of 4 is 1. With cycles. And then I continue with whatever I'm missing. So, I don't know, for example, I'm missing 2 right now. So let's start with 2. Pi of 2 is 2. So I close the cycle right away. Then I guess the smallest thing I'm missing is 5. Pi of 5 is 8. And pi of 8 is 5. So I close the cycle. Now I'm missing 7. And pi of 7 is 7. So I close my cycle. Okay? So it's a cycle notation, and you won't have any difficulty if I give you this to get the 1-line notation back. Or the 2-line notation. And finally, let's talk about digraph notation. So the word digraph actually just means directed graph. So what this is a graph where the edges have an orientation. Okay? And digraph notation is basically just a picture of this. And so I just say, okay, you know, I have 1, then 1 went to 3, 3 went to 6, 6 went to 4, and 4 went back to 1. Okay? Then 2 went to itself, 5 went to 8, went to 5, and 7 went to itself. Okay? So depending on what we're doing, we're going to be going back and forth with all these different notations. They're all going to be useful at different points. Okay? Mostly these two. These are the ones that we're going to use the most. So let's talk a little bit more about cycle notation. So one thing that I want to point out is that the cycle notation of a permutation is not unique. Why is that? Because I chose pretty arbitrarily which cycle to list first, for example. I started with 1, but I could have started with 2. Let me just write it over here, because the camera is facing over here. So, for example, what's a different notation for the same permutation? Well, I could switch the order of these guys, right? Put the 7 here, the 2 here, that's the same permutation. You could move the cycles around in whatever order I want. And more than that, I can actually change the order that I list these guys in. Because instead of going 1, 3, 6, 4, I could go like 6, 4, 1, 3. It's the same thing, right? And so, and actually you could count how many different ways of writing a particular permutation there are. But so what I want to do is fix what's called the standard representation. This is meant to be representation. It's impossible to read. Standard representation. So out of all the different ways of writing this permutation, we're going to choose a particular one. Okay? So I'll tell you what, the first thing we're going to do is that in each cycle, we're going to put the biggest number first. we can always do that, and I just did it here, right? I started with the 6 as the biggest guy, and you can always cycle around and put the biggest guy first. Here 6 is the biggest, here 7 is the biggest, here I need to switch these two. And then 2 is the biggest in its cycle. Okay? So that fixes in each cycle what the order is, but I also want to decide what order to list the cycles in. Okay? And so the way that I do that is that I do it in an increasing order of that biggest guy. So I start with the 2, which is the, so out of these maximum, I start with the 2, then for the next cycle, the next biggest is 6, then 7, and then 8. Okay? So the point is that these guys are in increasing order. Okay? And each one of these guys is the maximum in its cycle. Okay. So I hope we agree. We can always do this to any permutation. We can always do this, and there's a unique way of doing it. Okay, so this is what we call the standard representation of the permutation. Okay. So this will be very important in a little bit. Okay, so let's start counting now. So what statistics can we associate to a permutation? I mean, the first thing is that we should say we do know how to count permutations. We already did it, it's very easy. There's n factorial permutations. But we want to introduce some statistics, so can you think of some statistics for permutations?
Number of cycles.
I'm glad we didn't, I'm glad you said that. This was actually my number 1, even though there's many possible things. So one thing that you can do is say number of cycles. Can you tell me other ones while I write this?
The parity of the cycles.
Parity of cycles, so for example, number of cycles of even length. Or, I don't know, you can measure how much it goes up and down. There's many things you could do. But let's start with number of cycles, which is a very important one. So we're going to say that let C of nk be the number of permutations of n having k cycles. Okay. So we want to figure out what these numbers are, and let me go ahead and introduce another notation. Or maybe I'll introduce it up here because it's not too important to us right now. But it's good for you to know that there's something called little s of nk, and it's this thing with a sign. And these things are called Stirling numbers of the first kind. So the Stirling numbers are basically the answer to this question, except the Stirling numbers have minus signs sometimes. Okay? But anyway, so we want to compute this C of nk. And again, we should go back to the first class and think, okay, well, what exactly does it mean to compute this number? There could be several different kinds of answers. And we're going to do at least a couple of these. So one kind of answer we can give is a recursive answer. does this remind you of? This, it's somewhat similar to Fibonacci, and it's even more similar to something else that we saw. Especially if I cover this up, this is exactly the recurrence for binomial coefficients. So it's kind of worth, maybe I'll write it down over here. It's a good analogy to compare with and choose k. It's very similar. And the proof is going to be similar also. By now, we've learned to do proofs like this. We kind of analyze what happens with the last number. So we're going to split the C of nk permutations in two types. So the permutations of n with k cycles. So if n is in its own cycle, so if n is in its own cycle, then what can I do? Well, I can just throw that out, and what's left? The rest is a permutation of n minus 1 with how many cycles? Well, I just threw one of them out, and so I have k minus 1 left. Okay? And so that means that there's this many of
But
that.
what do you mean n is in its own cycle?
So what I mean is that if you look at the whole cycle notation, there is a cycle that only contains n. Like over here, 2 is in its own cycle, 7 is in its own cycle. And so what I'm saying is that if 8 was in its own cycle, then I could just delete it, and the rest would be a permutation of 1 up to 7. Okay. And so this gives me this many permutations, which is what I have here. That's a good sign. Okay. Otherwise, what should I do? If n is not in its own cycle? Well, let's just take it and just erase it from the cycle notation. Erase n from the cycle notation. What do I get? I get a permutation of n minus 1 with how many cycles? With k cycles, right? Because I removed only one element of a cycle that has several things. Okay, so that's C of n minus 1 comma k. So how can I explain this factor of n minus 1? Well, you see, the thing is that if I take my permutation of n and I delete the number n, then I get a permutation of n minus 1. But the question is, if I give you the permutation of n minus 1, how many permutations could this come from? So to get my original permutation back, what can I do?
You can add the n to any of the cycles.
I can add the n anywhere in my permutation. How many places are there to insert it? Well, I need to add it after somebody. Or let's say before somebody, right? Let's say I decide phi of n is something else. So that means I insert n before somebody. So I just insert n before someone. So what do I mean by someone? I mean one of the other n minus 1 numbers. Before one of the n minus 1 numbers. Okay. And so that means that of this type there are n minus 1 times c of n minus 1. Okay.
Pero si los mete detrás de alguien no está faltando un caso cuando lo ponga de...
So the question is, if I insert n before somebody, am I not missing the case where n is at the end of the cycle? The thing is, you have to remember these are cycles and they don't have a beginning and an end. So being at the beginning of the cycle is the same as being at the end of the cycle. Yeah. If I take, I don't know, 6, 4, 2, and I insert 8 before, it's the same thing as if I take 6, 4, 2, and I insert 8 again. Because this means 8 goes to 6, 6 goes to 4, 4 goes to 2, 2 goes to 8. This means the same thing. So that's why there's exactly n-1 places where I can put it. And so I take these permutations, I split them into 2 types. For one type there's this many, and for the other type there's this many. So that proves the advantage. End of proof. Okay. So this gives me a recurrence, and it's a good recurrence. And you can easily run this recurrence and compute a lot of these Stirling numbers. Okay. Now, another thing that I can do is to write down the generating function. The generating function for the Stirling numbers. And again, there's several ways of doing this. But what I'm going to do is that I'm going to fix a value of n and write the generating function for k. So I'm going to sum over k c of nk x to the k. So this is the generating function for these numbers. K goes from what to what? Well, these are the cycles of a permutation of length n. So the number of cycles has to be between 1 and n. Okay. And so this would be the generating function if I fix n. And if you didn't know the answer to this, what would you do? I think that the first natural thing to do is just to kind of write down some examples and see if you see a pattern. So you write it for n equals 1, for n equals 2, for n equals 3. And if you look at this closely enough, you're going to find the pattern. It's a very nice pattern. Actually, this answer is really kind of remarkable. What you get is this. It almost couldn't be nicer. Or you could think of it in the other way. I mean, I don't know, maybe some of you have to teach pre-calculus and you have to teach students to multiply x plus 1 times x plus 2 times x plus 3. And it's a natural thing to just multiply this out. What are the coefficients of this very, very natural polynomial? And the coefficients of it are exactly the Stirling numbers. And I think this is one of the reasons that Stirling numbers are very, very old and classical and very well studied. Okay, so I see your smiles. I see that you like this fact. I like this fact very much.
You know the numbers, like the first bunch of numbers of the Stirling numbers.
I don't know them by memory, but again, the easiest thing to do would be just like give this to whatever software you want, and just have it multiplied out, and you get the Stirling numbers immediately. How do you prove something like this? You should get used to the fact that in combinatorics, things like this have a lot of proofs. We're going to do one proof, and it's the easiest proof. Because we have a limited amount of time, and I just want to prove this to you. And maybe before proving it, let me ask you, what does this remind you of? If we're supposed to compare this with n choose k, then what does this remind you of?
Binomial theorem.
This is like the Stirling analog of the binomial theorem, right? If you put n choose k here, this would be x plus 1 to the n. And so this is like the Stirling analog of n plus 1 to the n. This is like the binomial theorem. And it's very useful to make these analogies because given that we know how to prove the binomial theorem in so many different ways, probably every such way can be adapted to prove this fact. And what's the kind of no-brain proof of the binomial theorem?
Induction.
Induction, right? It's also the ugliest, but if you really have to do it and you have to do it quickly, you can do it like this. And this works here also. By induction. So I'll ask you to believe me that the initial case works out, and let's just do the induction step. So let me take this thing and write it like this. Right? We know what this is by induction. This is the generating function for Stirling numbers for n minus 1. And this has to work out, right? I mean, at this point you know this is going to work out, you just have to do it right. This goes from k equals 1 to n minus 1. Now, what do we do? Well, let's see how we can get an x to the n and x to the k out of this. How can you get an x to the k out of this? In two ways. When you multiply this by this, do you use the x or do you use the n minus 1? If you use the n minus 1, then what should you multiply it by to get an x to the k? Exactly this guy. N minus 1 c of n minus 1 k. That's if I use the n minus 1. If I use the x, then to get x to the k here, I need to use the term x to the k minus 1 here. So what I get is c of n minus 1. And this is the Stirling number. Okay. So this is, I don't know, kind of the, when you get excited and you have a theorem like this, maybe you just want to prove it really quickly, this is a quick proof. But there's many other proofs. So let's talk about a couple of other kinds of proofs that you could try out. So here's one thing that you could try to do. One thing that you could try to do is compare the coefficients. Okay, so this is proof 1. But other proofs, proof 2, proof 3. Let me just give you at least two other ideas of how to prove this. So here's another solution. You could find the coefficient of x to the k on the right hand side. So what's the coefficient of x to the k on the right hand side? Well, in order to get an x to the k out of this, you have to choose, when you multiply one term from here, one from here, one from here, one from here, you have to choose k times x and n minus k times not x. Right? And so that means that you're going to choose n minus k of these numbers and multiply them. And so when you get the coefficient of x to the k, it's going to be the sum of all ways of multiplying n minus k of these numbers. And so what you would need to prove is that c of nk is the result of that. Take the numbers from 0 up to n minus 1, choose n minus k of them, multiply them, and add all the possibilities. It's harder, maybe it's more interesting, and it's possible to prove it like this, and this proof is in the book, so I recommend that you look at it. Let's talk about, okay, so that's proof 2. It might be worth it for you to rewind the video and see what I just said a little bit more slowly if I said it too quick. Proof 3. What's another way of proving this? There's a very nice way of proving things like this with combinatorial polynomials, which is to say, what if x was an integer? Imagine that x was an integer. Then you can easily invent a combinatorial problem whose answer is this. Find the number of ways of making a word of n elements such that the first word is between 1 and the first letter is between 1 and x, the second number is between 1 and x plus 1, the third number is between 1 and x plus 2, etc. X is an integer. So this is the answer to some easy combinatorics problem. what's this? This is like saying, okay, what's the number of ways of choosing a permutation and then giving each of its k cycles one of x colors? So this is like saying, consider a permutation and to each cycle assign a color between 1 and x. The number of ways of doing that is this. And so you have to show that the number of ways of doing what I just said is also equal to this. Having done that, you will have proved this for integers x. But the thing is that if this identity is true for every integer, then this identity is going to be true for the polynomials. And why is that? Because, you know, if you take the polynomial this minus this, you have proof that every integer is a root of that polynomial. But polynomials cannot have infinitely many roots unless they're the zero polynomial. So again, I encourage you to slow the video down and parse it, but I think that's another very useful idea. When you have identities for polynomials, you can just prove it for when x is an integer. And then you can try to find the combinatorial proof. And like I said, this also works out, and you can read it in the book. I don't know, actually he gives 4 proofs in the book. And one is this one, and the other ones are other ones. So you should look at them.
Y para series de potencia.
If this was, so the question is what about power series? If this was an identity of power series, then you can't really plug in an integer into a power series usually. And you run into issues of convergence and at least if you can make that work, it's going to be a lot harder. I mean, there are functions that have infinitely many roots that are not the identity, like sine of x. Right? Sine of x is 0. Actually, sine of 2 pi x is 0 at every integer. And so that's one reason why this doesn't work so obviously. There's many reasons why this doesn't work so obviously, but it's a great idea that might work if you're more careful than we are being at this moment. Okay. Anyway, cool. So that means we know how to count permutations according to the statistic of number of cycles. Okay. So maybe what I'll do next is so I want to show you, okay, so we said C of nk is the number of permutations of n with k cycles. Now, if you're taking notes, you should leave a little bit of space here. You know you don't need to take notes because I give you my notes, but do you have a question? So I want to show you a very nice trick for permutations, which sometimes is called fundamental bijection. And we denote it by a little hat. And maybe the easiest way to do this is just in an example. I think that's the clearest thing. So let me take a permutation written in cycle notation. But it's important that you notice something that I did here, which is that I wrote this in standard notation. Right? So it's important that these biggest numbers of each cycle are at the beginning and they increase. And I'm going to do something very weird that might sound a little bit ridiculous, which is that I'm just going to erase the parentheses. Maybe it's worth keeping the colors. Although, of course, the colors are just a visual aid. Okay, so that's strange. If this is W, this is W hat. And this is what I do in general. I take a permutation, I write it in cycle notation, in standard cycle notation, and I erase the parentheses. This is the fundamental bijection. Okay, well, it's fine. You can always define functions, but the question is if it's useful. And maybe the first question is this really a bijection? So why is this a bijection? In other words, if I stand in front of this, how do you know? Well, okay.
No,
Because no the colors.
You don't have the colors.
You don't have the colors. I mean, I guess the question is exactly how do you know the colors? Right? Because, right, so the question is if I give you W hat, how do you get W? But I don't give you W hat with the colors. Once you have the colors, then you know you just open a cycle whenever you see a blue guy. But the question is, how do I know that these guys should be colored blue and the other ones should not be colored blue?
The first one is always blue.
The first one is always blue.
And then each time you change, like,
One is less than the first one, then you picture that, you paint that color.
each time you increase,
Yes.
you paint.
So one thing that we know is that these guys should increase, right? 2, 6, 7, 8. They should increase because we listed these guys in increasing order. Okay? But why is it not 2, 4, 7, 8? Those also increase. Because the 6 went first. So my question is, what are the numbers 2, 6, 7, and 8 in this permutation?
The ones that are bigger than all the previous ones.
Is what we call the records of a permutation. The tallest guy that you've seen so far. So you start from left to right and you say, what's the biggest number that you've seen? 2 is the biggest that I've seen, blue. Then 6 is the biggest that I've seen, blue. Then these guys, okay, I'm not so impressed, I've seen bigger guys. And now here, this is the tallest guy that I've seen. And then this is the tallest guy that I've seen. Okay? So these things that I colored are exactly the records of the permutation, the kind of partial records. It's like a competition where you just see who's winning so far. So that's the point, that these guys can note that the blue elements it's a little bit hard to see the blue in the film, so let me note. The blue elements of W hat are the records. And the record is just the biggest number, those bigger than everything to their left. Every number to their left. Okay? And so that means that what is hat inverse? But if I give you a permutation, all you have to do is look at what the records are, color them in blue, and then just insert a parenthesis. Start a new group every time you see a blue element. So that's why this is a bijection. And in fact, what we just proved is that, okay, so first is that this is a bijection. And the other thing is that it sends W with k cycles to to W hat with k records. Because the cycles are in bijection with the records. The cycles of W are in bijection with the records of W hat. And so this is good. This is a bijection and it has some nice properties. And in particular, we get a theorem for free. What is that theorem? The theorem is that this is the number of permutations of n with k records. And so, one way of saying this is that number of cycles and number of records are equidistributed. And this is just like in probability. They have the same distribution. Exactly the same number of permutations with k cycles and with k records. And so you'll see this is a great tool. And very often you have a theorem, and by applying this bijection, you're going to get another theorem for free about permutations. Any questions about the fundamental bijection? So you might have seen already that there's a problem in the homework about this that I think is very interesting, which is to count the number of permutations that are fixed by this operation, which is very strange, right? Because here we're in cycle notation, here we're in one-line notation, but the question is, when is it that the permutation is the same when you read it like this and like this? And the number of those permutations is the Fibonacci number. So that's one of the homework problems. It's a nice problem. All right. So that's it about cycles and records. And let's see. Yeah, maybe I have time to do a little bit more about this. But maybe the other thing that I want to mention is that there's a different way of writing this that I want you to see it so that you start getting used to it. This is the same thing as writing sum for the permutations of Sn x to the number of cycles of those. So why are these two the same thing? It's by definition. It's by definition because to get an x to the k, you need to have k cycles. So that means that x to the k appears exactly in k times. So these are two different ways of writing the same thing. Okay. So maybe you're impressed now that we can count permutations not only by the length, but also by the number of cycles. But you've seen it in mathematics that we do two things. If a problem is too hard, we invent an easier problem and we solve it. And if our problem is too easy, then we invent a harder problem and we solve it. So given that we could solve this one, that means that we're going to go for a harder thing. Very typical in mathematics to do this. So what I'm going to say now is not only, and this is related to something that somebody said about not only caring what the number of cycles is, but for example if they're even or odd, or if they have a particular length around. Okay? And so I actually want to count the number of cycles that have, the number of permutations that have cycles of length 3, 2, 4, 5, 2, 3, 4, etc. I want to give you the length of the cycles and I want to count the number of permutations. So I'm going to say that the type of a permutation is a vector C1 up to Cn, where Ci is the number of cycles of length I. And so, of course, the sum of the Ci's is the number of cycles. Okay? And I want to ask how many permutations. So I want a theorem like this. There are this many permutations of type C1 up to Cn. Okay? So I give you the length of the cycles, you tell me how many permutations there are. It's actually not too hard. And the answer looks like this. And again, you should always wonder what's the best possible answer. In this case, I'm going to give a very explicit answer. And I think you'll agree that it's a lot as good as we can hope for. N factorial divided by 1 to the C1 factorial, 2 to the C2 factorial. So, pregunta? So this is the number of permutations with a certain type. Let's give an argument. And while we do the argument, let's do an example. So let's say that my type is 3, 2, 1, 0, 0, 0, 0, 0, 0. That's a type. And so I want to have 3 cycles of length 1, 2 cycles of length 2, 1 cycle of length 3. So to build such a permutation, what do I do? Well, I know what I need to do, right? I need to have 3 cycles of length 1. I need to have 2 cycles of length 2. And I need to have 1 cycle of length. Fill in the cycles. Okay. How many ways are there of filling this out? It's not a trick question, it's a very easy question. It's just n factorial, right? Because you know you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And so you just need to put the 10 numbers in there somewhere. And maybe we'll do it like this. I don't know. 4. It doesn't really matter how you do it. So put the 4, the 8, 10, the 2 and the 5, the 3 and the, say the 6 and the 3. What am I missing? The 1, the 8. From the 8, where to put it down?
9 and 7. 9 and 7.
7. Okay. So there are n factorial such fillings. So why is the answer not just n factorial? Well, because different fillings are going to give me the same permutation. So how many fillings give me this permutation W? This is W. How many different fillings, in other words, how many ways of putting the black numbers in are going to give me the same permutation? Well, for example, you can permute these three guys in any way. 4, 8, 10. Here there's 3 factorial ways of writing 4, 8, and 10 in whatever order you want. Right? These two, you can list them in whatever order you want. So that's 2 factorial. Either this goes first or this goes first. And this one, okay, this is kind of silly, but 1 factorial. What numbers did I just write down? These are C1, C2, and C3. And in general, I have C1 factorial, C2 factorial, up to Cn factorial. But are there other permutations that give me the same W? Well, yes, because here I could write 2, 5 or 5, 2. So there's actually 2 possibilities here for how to do this. And here I could write 6, 3 or 3, 6. 2 possibilities. What about 917? How many ways are there of doing that and getting the same answer? 3, right? You either write 917, 179, or 791. And this is a cycle, and you just need to decide who you put first, and then the other ones are forced to be in cyclic order. So here, there's 3 ways of writing this little cycle. What did I just write down? And okay, again, it's kind of silly, but let's put the ones here, because each one of these can be filled in a unique way. And so what did I just write down? 1, 1, 1, 3 times, that's 1 to the C1. 2, 2, 2, C2 times, and so on. Okay. And so what did I just do? I just wrote a mapping from all the permutations to the permutations that have the type that I want. This is a surjective map, and for each one of these guys I have the same number of this kind. So this is what we would call I don't know, let's call this number n. So what I have is an n to 1 mapping. Okay, so this is an. So what I did is to give a map from all permutations to, let's say, the ones that I'm trying to count. What I'm counting here. So this map that, and again, what is the map? You just write the permutation for A10 and just insert it into here. And this is an n to 1 mapping. Okay? And if you have an n to 1 mapping from here to here, that means that this set has to be n times bigger than this. Which means that this set has to be n factorial divided by n, a capital. So that's it. And I should say that there's a very nice way of writing this in the language of generating functions, but I'm a little bit short on time, so I'm going to skip it. But you should look at the generating function way of doing this in the notes. Esto se acaba a las 50, ¿es? So now let's talk about new statistics. So we talked about number of cycles, we talked about number of records. Let's talk about a very important statistic, which is the number of inversions. Statistic number 3, number of inversions. So what is this? An inversion of a permutation written in one-line notation is a pair Wi, Wj such that, I'll do this a lot in class, this means such that even though I is less than j, Wi is bigger than Wj. Okay? In other words, these are the pairs that are in the wrong order. The bigger one is before the smaller. And I'm going to write in of W for the number of inversions. Okay. And so maybe it's worth doing a small example. So what's the number of inversions of 2, 4, 1, 6, 3, 5? I just have to see who's in the wrong order. And we can start, for example, by saying, okay, who's in the wrong order with 1? 2, 1, and 4, 1. Who's in the wrong order with 2? Well, I already counted 2, 1. There's no others. Who's in the wrong order with 3? 4, 3, 6, 3. I skipped 6. But let's say that there's nobody before it. That's in the wrong order. And then, who's before 5 and in the wrong order? 6. So these are all the different pairs that are in the wrong order. How many are there? 1, 2, 3, 4, 5. And so, again, the goal is to, yeah?
That is always when we write the permutation in the one-line form.
Oh yeah, so it's important that here this is done in one-line notation. Yeah. Okay, so of course the goal again is to enumerate permutations according to the number of inversions. And let's say that the inversion table of W is this is a bad name because this is not a table. For some reason, they call this the inversion table, even though it's a list of numbers, where AI is the number of J. Let's see, what's the easiest way to write this? J such that Ji is an inversion. Okay? And so that's what we did here. So what is the, I think we call this I of W. So what is I of 2, 4, 1, 6, 3, 5? This is what we just did. So we say, okay, well, who's in the wrong order with 1? And before 1, 2 and 4. So there's 2 of them. Then before 2, there's nobody. Before 3, I had 1 and 2. Before 4, I had nobody. Before 5, I have 1. Before nobody. Before 5, I have 1. And before 6, I have nobody. Okay? So this is called the inversion table of W. So what's the next question that you should be asking yourselves? How to get the permutation from the inversion table if it's possible. Is it? Maybe, maybe not. Let's before doing that, let's talk about something else. What can you tell me about this number?
always
This is
zero.
always 0, right? 6 is the biggest number, so there's not going to be anybody to the left of it that's bigger. So this is always 0. What about this one?
Less or equal than 1.
It's 0 or 1, because how many numbers could be before 5 and bigger than 5? Well, at most 1. How many numbers could be bigger than 4 and to the left? 2. And so on. And this one could be at most 5. Okay? So, let's do a quick non-rigorous count. Does this have the hope of being a bijection?
With what?
With permutations? Because if we want to return, then this would be a bijection. Is it possible that this could be a bijection? How many permutations are there? 6 factorial. How many tables are there?
5 factorial.
It's actually 6 factorial because this is less than or equal to 5, but it could be 0. So this number is anything between 0 and 5, between 0 and 4, between 0 and 3, etc. So there are 6 possibilities for this one, 5 for this one, 4 for this one, 3, 2, 1. So the number of tables like this is also in factorial. And so this is some kind of optimistic evidence that this could be a bijection. And if you're looking for bijections, you should be sure that the two sets are of the same size. Right? Otherwise, you have no hope. And it turns out that it is. So, proposition, this is a bijection.
But isn't there always 1 when the two sets have the same number? Same size.
So the question is, if two sets have the same size, it's not a question, it's a statement, right? So you're telling me, if two sets are of the same size, there is a bijection between them. That's the definition of having the same size, actually. And that's true, but what will be true in this class is that we need bijections with good properties. We always want bijections that are nice and we can get extra information from. Okay? Because we're not just trying to prove that there are factorial permutations. We already knew that. But somehow we will get extra information out of this. So we're not looking for any bijection, we're looking for a bijection with nice properties. Okay. Let me. I'm a little bit short on time, so maybe what I'll do is just do it in an example. So proof by example. Okay, proof in quotation marks. But I think in this example you will see how to do this. What we want to do is construct the inverse. Right? Okay, so I want I of W to be 2, 0, 2, 0, 1, 0. Actually, people that are watching in camera have the advantage that they cannot see what W was. And that's good, because we don't want to use what W is, we want to derive what W is. And so what I'm going to do is this, I'm going to write a sequence of permutations. So that, I want A6 to be equal to 0. Well, actually, A6 is always equal to 0, as we said. There's no inversions with 6. Now, I want A5 to be equal to 1. So I'm going to write a permutation of 5 and 6 that satisfies this. Where should I insert 5 so that A5 is equal to 1? Remember, I is the amount of numbers to the left of I bigger than I. So I need one number to the left of 5 that is bigger. So that means that I should put the 5 here so that A5 is equal to 1. Now let's insert 4. Well, it's important that I know how much A4 is. A4 is 0. So where should I insert the 4 so that there's nobody bigger than it to its left? It has to be at the beginning. Then A3 is 2. So where do I insert the 3 so that there are 2 inversions with it? Well, they put a 2 after, right? So 4, 6, 3, 5. So you see what I'm always doing is putting the new number AI positions after the beginning. Okay, what about A2? A2 should be 0, so where should I put my 2? 5, 6, 5, 4. This is meant to be W3. W2, so it needs to be at the beginning, so that there's no inversions with 2. And then A1 should be 2, so where do I insert the 1? Again, I put it 2 after, so 2, 4, 1, 6, 3, 5. Okay? And that is the permutation that I started with. And I hope this sounds believable. I mean, it's clear that what I did really has the correct AI, so that if I apply the map I to it, I am going to get the sequence. So this is a bijection. Okay? Now, what's the point of doing this bijection? The point is that what's the number of inversions? How do I read the number of inversions from the inversion table? Well, it's just the sum, right? 2 plus 0 plus 2 plus 0 plus 1 plus 0. Okay? Now why is that nice? That's nice because my statistic from permutations to inversion tables behaves very well with respect to the statistics. Right? So we're going to go over here again.
¿Cuántos animales hay? Físicamente ir a contarlo.
So this is a bijection from Sn to, what is this? We said that the first number is between 0 and n minus 1, the second is between 0 and n minus 2, and the last one is between 0 and 0. Right? But this bijection respects our statistic, right? The number of inversions of W transfers to a statistic over here that's very nice. It's just the sum of the elements. Okay? And so why is that nice? Because we get a corollary for counting permutations by the number of inversions. Because instead of counting here, we're going to count over here. And that's easier. Maybe let's give the proof, and then we'll see what the answer is. So the bijection tells me that this thing is the same thing as the sum over A1 up to AN, where I is between 0 and n minus I plus 1.
What is LHS?
Oh, sorry, left hand side. Thank you for the question. Left hand side. So I need to sum over these sequences, and x to the inversions becomes x to the this. Okay? But I can write this as x to the A1, x to the A2, up to x to the AN. And given that this is a sum over n things, I can actually write it as a product of the sum for A1 from 0 to n minus 1 of x to the A1, then the sum for A2 from 0 to n minus 2 of x to the A2, up to the sum from AN equals 0 to 0 of x to the AN. So I take this sum over many variables and I split it into a bunch of sums that are actually very easy to compute, right? This is 1 plus x plus up to x to the n minus 1. Well, maybe we'll write it in the opposite order. What we get is 1 plus x plus x squared, 1 plus x cubed, x squared, x cubed, etc. to 1 plus x squared. Which again is about as nice of an answer as we can hope. And so again, if you want to count the permutations with a certain number of inversions, you just multiply this thing out and see what the coefficients are. And you will have your answer. Okay? And just as an easy check, what happens if you put x equals 1?
You get n factorial.
Here you get n factorial. Here you get 2 times 3 times 4, which is good, right? We should get an equality. This thing is really beautiful. And by the way, there's a different way of writing this because, as you know, these are geometric series, so I could write this as x to the something minus 1 over x minus 1. These numbers are going to appear a lot. And let me just write very quickly. And I'll explain a little bit more about this later. That the number 1 plus q squared plus q to the n minus 1. Sometimes people just write it as n sub q.
I have a question. If you replace x with 1, you get n factorial over there. I don't understand.
So let's go back to the question of what happens when I plug x equals 1 on both sides. So when I plug x equals 1 here, I have a sum of 1. This is always 1. And there's n factorial permutations. So that's why this is n factorial. And the reason that this is n factorial is that when I plug x equals 1, this is 2, this is 3, this is 4. So let me just say that this thing is called the Q analog of the number n. Sometimes people say quantum analog to make it sound fancier. And this number, then, what we have here is 1 sub q, 2 sub q, n sub q. Well, that naturally we should be calling it n factorial, with n factorial sub q, and this is the q analog of the function factorial. Okay. And we will say a lot more about why these numbers really behave a lot like, for a lot of purposes, this is almost like an n factorial, this is almost like n. We will see more about it. But anyway, so that's it. So we enumerated permutations by cycles, by records, by inversions. And we will do more enumerations next time.